Okay. So we have a data cube with 2 spatial and 1 temporal dimension. You could also have additional dimensions as well, but this is what we conceptualize as a data cube. And in our data cube, let's have a look at one observation, 1 pixel inside, what is in there. We have the spectral signature, that's the reflectance measured by the satellites. But this is not so easy to use, and you need specific algorithms and so on. So what we have in addition from the semantic enrichment, the categories that are also in there associated to the spectral signature. Then we may have some continuous variables that gives us an idea about how bright the pixel is or how green a pixel is, which could be useful for vegetation analysis, for example. And we may have some additional geographic data, for example, the altitude at which the pixel is located. And this is all referenced in space and time. And what you can do now is you can create a query, a semantic query that uses all of these information or all of the data that's in here to get to new information. For example, you can select a specific categories or pixels with specific categories, then use these pixels to calculate something with the continuous variables and so on. So this is all prepared in the data cube. So how does our high-level semantic querying language works? The base component is the categories. So let's just pick a random example in Austria. This is now a simplified example, but it shows quite well, I think, what the idea is. We travel back in time and we start in the past and continues until today. We may observe a category that's weak or young vegetation, which is fine. Maybe the early state of the year. Then we have strong vegetation. The vegetation is growing, so that's fine. Then we may have an observation with cloud, but we can handle that because it's categorized in our data cube. We can remove the clouds if you want. The next observation may be still strong vegetation, which is also fine, but then maybe something happening, and we can then identify what's in there, or we can go the other way around and we can specify this pattern as a, let's call it search pattern in the semantic model, and then we can identify the areas where these type of changes happen. And this nice example shows that the knowledge you can bring in as a human to the system is very useful to make this type of query not only technically possible, but also explainable to non-experts in this case. This change of categories can be communicated. So we have this in our data cube, this 2 approaches. So the first one is the semantic enrichment. This is a bottom-up approach, and this is combined with the top-down semantic querying, basically the knowledge-based approach. And this is brought together in the so-called inference engine that evaluates the semantic model and this high-level query into the data cube queries. You see this is possible in the graphical way, but also in a programmatical way. So we have an API, but we also have this graphical user interface where you can create the graphical queries at this point. So how does it look like here? You see a screenshot of our the front end of our system, the graphical user front end that allows to do these inferences or the information extraction using semantic querying. You just need a web browser, and the queries that you create are sent to the server. This front end is generic, so it doesn't only work with our data cube. You can work with other data cubes as well. as long as they are semantically enriched, and I share explain to you how that works. So in our queries, you have or in our data cube, you have attached to that a so-called knowledge base where the semantic models, again, this is an example, a graphical example, where they are stored. And this applies this algorithm that you define in a graphical way to the data cube and creates the output. We published this approach, particularly the inference engine, as an open source code. So if you want to be interested in that, you can have a look. Just a very quick technical overview how that works, because there's some important ideas in there that we think need to be considered. The first one is we bridge the semantic domain and the image domain. So the semantic domain, you have entities like a forest or lake and so on. They may be defined, but not based on what you can see in the image. And the semantic entities, the categories, are obviously, they exist in the real world even if they are not captured by an image. So the semantic, the world is existing in at the one side, and then we have the image domain where we also have dimensionality reduction, because we don't have the 3 dimensions anymore. We're looking down from space. We have only 2 dimensions. Try to recover the third, the temporal dimension as well, with multiple observations. So we have to separate the semantic and the image domain, and we need to try to bridge that back to a harmonized view. This is the conceptual overview how that works. So basically, as a user, you define the semantic concepts in a let's call it ontology, and on the other side, we have the semantic enrichment that creates the variables, the categories that you can use, and then you create a mapping in between these 2 worlds. So conceptually, these 2 domains are separated from each other. The user is creating in more or less their vocabulary, their language, the queries, and then this is translated into the image domain. Our implementation is based on Python, and it's data cube agnostic. So you could potentially use different data cubes for that. We have, as already explained by Dirk, we have used the Open Data Cube as an implementation case, but this is really independent. What you can see is that there's an abstract data cube class, and you can create own classes here to extend it. As an example, what we can do is obviously Greg showed that very nicely, of very high interest, the vegetation status, how green is Austria. We can create these type of information layers here, and you see the brighter the color, the greener, or the more often vegetation was observed, and you see very nicely the lakes and the mountains and the rocks where no vegetation is, but you also see the impact of the cities and the infrastructure and so on the vegetation. So we can create this type of information layers. Again, on the right side, you see the semantic model that has been applied to generate this information layer at this point. Some other examples that we investigated: landslides. So you see here from the top to the bottom the landslide where the soil and the mud was going down the mountain, hitting the infrastructure, the road here. We see the storm damage on the left side. You see the situation before the storm. On the right side, you see the situation after the storm. All the blue areas are affected by storm damages. And then what may be even more important is we can track the vegetation growth after the storm damage in the next, let's say, 10 or 20 years with this. Soil sealing is also a very important environmental topic that we can identify, or we also use this for agricultural monitoring. I show you an example how this works in real in our data cube. So you have the knowledge base and the fact base. The fact base is the data cube. The knowledge base is the semantic model, and you select the data cube that you want to work with. You select the semantic model from the knowledge base. It can also be shared with other users, so you don't have to be an expert in your own topic. You can use a semantic model that has been generated by someone else, and this is done with this nice drag and drop solution here, where you can configure that on your own. As a next step, you select your area of interest and the time of interest from the data cube. In this case, it is a agricultural field in Austria. What we want to do with the analysis is to identify the changes from vegetation and bare soil with this type of analysis. It's a selection of the time interval that we're interested in. In this case, we are interested in the spring and summer months of a year 2002. We send this inference or the request to the cloud, where it will be evaluated, and then we get the results like this. In this case, it is a map showing different vegetation and bare soil percentage, and you can use it. I jump a bit to the second example, because what allows us, or what the semantic enrichment allows us to do, is because it works worldwide, so we can set up a different data cube somewhere else. And in this case, we use exactly the same model and apply to this area as well, which should generate a similar result, but obviously with a different content. So this is our approach to make these queries transferable across different data cubes, across different parts of the world, as long as the semantic enrichment is the same. And you see the result looks very similar. Here we see agricultural fields. They are probably also irrigated here at the border between Syria and Turkey. So I stop here. Well, maybe this is interesting as well. The two curves that we can generate it in addition. So Greg showed that very nicely. Thank you for that. For the different outputs you can generate from a data cube. It could be maps if you aggregate over time, or it can be curves, and you see that very nicely where the vegetation, so the bare soil and the vegetation curve are replacing each other, let's say, so you can see the vegetation growth at this place. What I want to continue is with this view on different clients, because we think that these type of analysis should be more or less everywhere and should be accessible from different clients. And this is the reason why we developed this interface and this API, the application programming interface, that can be connected from various clients. In our data cube, we have a standard JSON API that consumes the ID of the fact base, the ID of the model, the area of interest, and time interval, and you can send this to the server, and you get the results. So we don't have a specific interface here. We can use the standard API for that, and we can integrate these analysis either directly or cached into different applications, like a mobile application, smartphone applications, command line interface if you want to schedule something. We also have a full ArcGIS Pro integration where the output would then directly be inserted into the project. What I want to conclude is zooming out a bit. Greg mentioned that already. The Earth observation data cubes can have quite a significant local impact. We have seen that with the examples in both talks. What it also allows to do is adding own data sets that may not be available in the big portals, or you may not be able to share them because they are protected or sensitive. So these type of self-managed, self-hosted infrastructures allows you to do that. In our case, we also have seen that it's possible to extend this as a midstream technology, so you don't have to rely on what is provided to you. You can adjust it, you can change it to your own needs. And once you have this local data cube, you can make use of local knowledge, integrate communities in the building process. You can integrate the people that are really also affected and part of this development in the local environment. The main challenge here remains still the interoperability and the transferability. I was very appreciating that Greg was showing also some parts of reproducibility and these type of scientific challenges. So now you may ask, can we really have a local impact or an impact at all? I think that's quite clear now after the two talks.